Let's talk a little bit now about a few applications of Faraday's law. And the first one, perhaps most familiar, is a transformer, right? Transformers are very common across the power grid. They're used in lots of audio components as well. And they basically operate using Faraday's law. And the idea of a transformer is that you have two coils of wire, and through one of those coils, called the primary, you basically are injecting a current of some sort. The current is rolling around and spinning around in a circle. In doing so, you are generating magnetic fields. Magnetic fields will pass through the coil that you're creating. And then you have a secondary coil that is designed to pick up those same magnetic flux lines and convert those into another current on the other side. So this is a way to take a current in one place, yield another current on the other side, and have those two isolated from each other. It's not electrically attached. So it separates those two currents from each other electrically. You have to put in some sort of a sinusoidally varying current, or not necessarily sinusoidally, but some kind of a time varying current into this wire, and it will be picked up on the other end. The other important piece of this is that these transformers are often built around what's called a core. A core is going to be a very high permeability material that basically is going to trap the magnetic flux lines inside, much like a dielectric for electric fields will trap electric fields on the inside, or electric flux lines. So will be true for a high permeability material that will trap magnetic flux lines inside. And so that ensures that the magnetic flux lines generated by this primary current will flow and stay within the magnetic flux lines and will then pass through this secondary current. Now, if you think about as the current is varying in the primary sinusoidally, that also means that the magnetic flux that is passing through this square on the other side is also going to change sinusoidally. And so the time derivative of that is also going to be a sinusoid. Since if I take the time derivative of a sine wave, I get another sine wave. And so we'll be producing the same current inside of the secondary winding. And the reason you can show that is that, remember that electric field lines are going to swirl around the time variation. And in this case, the time variation is up and down, as shown in this diagram, or perpendicular to the secondary current coil. And so that's going to give us electric fields that swirl around, which means it's going to be in the direction that that coil is oriented. So this is one way to take a current on one side and flip it and make a current on the other side. All right, let's also talk about inductive charging. For example, wireless powers. Increasingly, phones have this, but there's various applications for inductive or wireless power charging. And the idea is pretty simple. All you really need is two different coils that are sort of physically pretty close to each other. And all you got to do is you run an alternating current through one coil, and again, through Faraday's law, it's going to appear as a current on the other one, and then that current you can use to charge a battery. So even though you don't have any physical touching between the two coils, you can still basically cause currents to jump from one to the other. And this obviously is very useful for wireless power transfer without having to physically attach something. Increasingly in cars, we're starting to see more use of what are called induction brakes or eddy current brakes. And this is actually an example taken from a bullet train in Japan. And they actually use a magnetic braking system that uses what are called eddy currents. Eddy currents are basically this notion that if you take a permanent magnet and put it over the top of a magnetic material, you're going to have sort of fast currents that spin around in a circle in that material. And so if you bring that magnet very close to the material, then if that material is moving, or if the magnet is moving with respect to that lower material, all those eddy currents are going to form. And then as the magnet is sweeping by, you have a change in the magnetic fields or the magnetic flux lines that are through this material. And so currents are then going to be created that go in the opposite direction and try to oppose the fact that this permanent magnet is moving, and that will actually slow your train down significantly. And this is sort of a clever way to slow down without using sort of a physical brake or a physical touching, as has been used before. And this concept also is now increasingly being used in electric vehicles, or both hybrid cars and more recently EVs. It started out with sort of hybrid cars in the early 2000s that implemented these regenerative braking systems that instead of having a physical contact between a brake pad and your wheel in order to slow you down, instead you had a coil of wire and you would activate that coil with a current through it, and that would basically oppose the continued turning of this wheel, since as the wheel turns, it's changing the magnetic flux that's through this coil. And so then you're drawing energy out from the tires and you're channeling it via currents, and you can use that to charge a battery, and that battery can then later be used to charge an electric motor. That was the idea of how hybrids work. Electric vehicles that don't even have internal combustion engines at all basically primarily use what they call regenerative braking, which again is this notion that when you press on the brake, perhaps you could have a physical contact, but your primary way of slowing the car down is to capture the energy from the tires and direct it into a battery that's charged up. And the way you direct that is, again, with Faraday's law, that you have to have some kind of a permanent magnet turning, and you've got sort of a coil of wire running current through it, and you'll be generating additional currents in that coil of wire whenever whenever the magnetic field through it is changing. So that's again sort of an increasingly heavily used application of Faraday's law. It just simply relies on this fact that if I have any sort of area and I have magnetic flux lines through that area changing, I'm going to generate currents around the outside of that area. Right, so that's just a quick few applications of Faraday's law. This has not yet gotten us to the point where we have waves yet, but we are halfway there. And in fact, to start out the next video, I'm going to show you an example of a way in which Faraday's law can already start to propagate signals from A to B, but we're going to need the other half of that in order to complete the picture of electromagnetic waves.